Sir Isaac Newton, famous for discovering gravity, finally understanding the motion of the planets, being a weird shut-in. Many things Newton is famous for, but one you might not know is that he was one of the first people to conceive of a device that we now know as the thermometer. See, Newton needed to understand what temperatures he should cast metals at in order to best work them. And he devised a scale involving brine and boiling water, much like we have degrees Fahrenheit today. What Newton would do is he would place molten metal on an aluminum planchet and try to see how quickly it heated the larger block of aluminum. So in order to decide on, or in order to understand heat conduction from one material to another, picture a small blob of boiling metal on top of a much larger block of aluminum. Heat is going to flow from the metal into the aluminum, so the whole aluminum will get warm while the metal reaches its temperature. Eventually, this whole system should be one temperature. Newton wants to try to predict what's going to happen, how that's going to work. And what Newton realized is that if I put this hot metal on top of a cool block of aluminum, imagine the block of aluminum is big enough that its temperature stays constant. We'll call this our baseline temperature. It's going to use the symbol T sub S. Well, it turns out if you put a very hot thing in a cool room or on a cool block of aluminum or inside a cool refrigerator, such that the temperature of the room or large block or refrigerator doesn't change, it turns out that the way that the hot thing loses temperature is by exponential decay. Now, this wouldn't be a very exciting lesson if exponential decay was the whole story. It turns out it's just 90% of the story. The only difference is that we've got a vertical shift by T sub S units. So if your refrigerator is 33 degrees and you put a meatloaf in the refrigerator, the meatloaf will cool via exponential decay, but it won't cool all the way down to 0. That would be ridiculous. It'll cool to 33 degrees. Or if your block of aluminum is room temperature 68 degrees and you put a 1500 degree drop of molten steel on it, okay, steel doesn't melt that cold. Sorry, a 3000 degree drop of molten steel on your aluminum, well, the drop of steel will cool exponentially down to a room temperature of 68. So what I need to do is take my exponential decay, y equals y0 e to the kt, and do a vertical shift by T sub S. So here's how this is going to look. This is an important point. Let's say this is the initial temperature T sub 0, yes? This right here. Well, then what I've got here is this is T sub 0, and this is T sub S. So that's our initial temperature and our room temperature. And what that means is when I make this coefficient y0, that's supposed to say, in a regular exponential decay problem, this length is y0. It's how far your initial value is from your asymptote. So in this case, our y0 is going to be this distance right here. It's going to be T0 minus Ts, because that's how far above room temperature our initial temperature is. It'll make more sense once I do an example, I promise. So altogether, Newton's law of cooling says the temperature in an object as a function of time is equal to that initial value, T sub 0 minus T sub S, e to the negative kt. We'll make k negative so that we always get a positive number for our cooling constant, plus room temperature, and that's our vertical shift. All right, let's go ahead and do a couple of real-world examples. I'm going to start with a fairly benign one. We're going to make Jello shots. So I'll start PG-13, and then we're going to take this straight into NC-17 territory when we find a dead body and try to figure out who murdered it. So let's start with Jello shots, shall we? Your recipe for Jello calls for 150 degree Fahrenheit water. That's how hot you have to mix the powder in to get everything to mix nicely. So we're going to pour the Jello powder into our big bowl of water, stir it all together. It's going to start out at 150 degrees. Now you've got a party that you're bringing these Jello shots to, and the party starts in 2 hours. We want to know, are we going to be late? So we put our Jello into a refrigerator. The refrigerator's set as cold as it can go. The refrigerator is 32 degrees. So for those of you keeping score at home, 150 is our initial temperature, 32 is our room temperature, because the room is the inside of the refrigerator. Now, just like before, there are 3 parameters here: initial, room, and K. We've already got initial and room, so we're well on our way. I need a 3rd data point. So we're going to tap our toes and drum our fingers and look at the clock impatiently. 1 hour passes. We stick a meat thermometer in our bowl of, well, it's not Jello yet, it's still liquid goop. Bad news, it's still liquid goop. Not only is it still liquid goop, it is still 95 degree Fahrenheit liquid goop. This is enough data. We have this point, we have this asymptote, and we have this point, 195. Are we going to be late to the party? I should mention one more thing. This Jello is never going to reach 32 degrees. It's going to get closer and closer, but it's never going to reach in it, which is good news because the box says solidifies at 40 degrees. Before you ask, no, we didn't have room in the freezer. It was full of goulash. Had to use the fridge. So the question is the Jello going to get below 40 degrees in time for our party in 2 hours, or are we going to be late? So I'm going to say part A, make a model. Part B, what is the temperature in 2 hours? And part C, when is the Jello done? So in part A, we need to make a model, and we're already most of the way there. My formulas, as you recall, T of T is T0 minus Ts, e to the negative kt plus Ts. And now I know my initial temperature was 150. My refrigerator is running at 32. So I've already got 2 of my parameters. 150 minus 32 is 118. E to the negative kt plus 32. And once again, as a reminder, we're taking an exponential function and moving the whole thing 32 units vertically, which means that this distance right here, what would have corresponded to y0, is not the whole 150, but just the 118, because 118 plus 32 is 150 degrees. So this is the point 0, 150. It's 118 units above the asymptote. That's why this number is 118 and not 150. Anyhow, we've got our information that after 1 hour, the Jello has reached 95 degrees. This will allow us to solve for K, which is the cooling constant that is unique to the composition of the Jello and the shape of the bowl it's in. And that will allow us to find out if we're going to be on time for the party. So we subtract 32 from both sides. 95 minus 32 is 63. Divide by 118. You know what comes next. Dedoy, Nathan. We know the value of t. I said I plugged in a 1. Well, k times 1 is really just k, so I'm going to stop copying the 1. K is the negative of natural log of 63 over 118. So I crossed out my minus sign, moved it to the other side. So I plug that into my calculator. K is approximately 0.62755. For party math, 5 digits is probably going to be appropriate. So, part A is complete. Our model says the temperature as a function of time is equal to 118 e to the power of negative 0.62755 t plus 32. Again, Newton was very much a shut-in. It's not known whether he ever moved more than 30 miles from his hometown. It is known that he never had a girlfriend. Perhaps equations like this are why he wasn't invited to so many parties. Anyhow, let's see, using Newton's work, if we're going to be late to our party. The temperature after 2 hours should be 118 e to the negative 0.62755 times 2. I'll put parentheses here to plug this into my calculator. Oops, that's not an equals sign. Nathan, that's a plus sign. Calculator says 66. At the moment the party starts, the Jell-O is still going to be an unusable, fruity flavored vodka soup. Actually, that doesn't sound half bad. At 66 degrees. Room temperature. Anyone want room temperature fruity vodka? I thought not. Let's see how long it's going to take for our Jell-O shots to reach the appropriate temperature of 40 degrees and solidify into the jiggly treats we want. The temperature as a function of time must be 40 degrees, but we don't know the value of t. So we're going to be late to the party. Let's find out how late. 0.62755 times t plus 32. Whoops. I wouldn't got the right answer there. I forgot my coefficient of 118. All right. Let's solve this equation for t to find out when the Jell-O will be done. Isn't this great, though? I mean, think about the implications. If you know that your soup needs to be 150 degrees to serve, if you have 2 data points, the temperature when it came off the stove and the temperature when you put it in the fridge, you can calculate precisely when the soup will be ready to serve. Better than keeping your guests in suspense and going back and forth to the fridge like some kind of nervous wreck. Is it cool enough? No. Is it cool enough? No. Is it cool enough? No. For Pete's sake, just use Newton's law of cooling. It will be cool enough in 32 minutes and 11 seconds, I guarantee it. Math is wonderful, folks. It's just wonderful. I'll subtract 32 from both sides. Divide by 118. You've seen these steps a million times at this point. I'll take the natural log. Oop, not E. Not E. 0.62755 t. And in fact, I'm not going to write it a whole nother line. I'm just going to cross that out, divide by it here. 0.62755. So that means that t is, plug this whole mess into my calculator. 4.288. Listen, if someone says, hey, when are you coming to Chad's party? And you say, I will be there in approximately 4.288 hours. That will be the last time you're invited to Chad's house and he's got a pool. Instead, we're going to say 0.288 times 60 is 17. So we could say we'll be there in 4 hours and 17 minutes. No, that's still weirdly precise. Let's go with 4 hours and 20 minutes. That's a funny number. Anyhow, that's it for our Jell-O shot example. Join me in the next video on this playlist for a dead body.